All right, let's take a look at question number 27. Question number 27 is, excuse me, one second. Sorry, there we go. Question number 27 is about a mass and a spring um, that we might set into oscillation back and forth here. And a key understanding to this question is it says here, there is friction between the block and the surface. So this is not an idealized system, but a real system. And this block and spring could go back and forth for some time, but we know because of friction, eventually the surfaces will heat up and all the mechanical energy in the mass or spring will eventually become thermal energy due to friction, and this whole system will settle down and stop at its equilibrium position sometime down the road. Um, so we're asked for looking for pairs of graphs, one that describes the energy of the block and one that describes the energy of the block and the spring. But let's be really clear about this. When the block is, say, as far to the right as possible, and it momentarily stops before reversing direction, so imagine it sort of in this position here, um, then as far to the right as possible, then the spring is compressed, and while the block has zero kinetic energy, the spring has a lot of elastic potential energy. And when the block comes through in the other direction and goes to the far right, we could say the same thing. The block now has um, uh, zero kinetic energy on the far left, and the spring is as expanded as it's going to be, so it's going to have a fair amount of elastic potential energy. And they're going to swap off elastic potential energy in the spring for kinetic energy of the block. When the block comes through to this equilibrium point and the spring is at its normal length, there's no extension or compression of the spring, and so it has zero elastic potential energy. And excuse me one second. Sorry, I had to sneeze. I thought I would spare you that. So when the block comes through this equilibrium position, it should have the spring should have zero elastic potential energy, and the block should have its maximum kinetic energy. So they're going to swap off one for the other, but the system should eventually come to zero energy. The entire system of the block and the spring should come to zero energy. Okay, so when we look at pairs of graphs, we're going to be looking for the energy of the block to be diminishing, but since it only has kinetic energy, there should be moments like this moment right here and this moment right here where the block has zero kinetic energy and is reversing direction. So let's take a look at what the possibilities are. This first one um, looks like it could be a reasonable description of the energy of the block, but this uh, can't be the block and the spring because the block and the spring have to kind of sum up to something that should be slowly changing over time. It won't be true um, that the energy of the block and the spring will come to zero and then come back to something. This might be a very good description of the energy of the spring itself. Notice that when the block is at zero energy, this graph here shows a high energy, so that could be the energy of the spring, and the two of these together could add up to give you the energy of the block and the spring. So we're going to reject that one because uh, the entire system can't go to zero and then come back from there. Okay. The next one. This is a description of a system where the energy of the block is diminishing, but the energy of the block and the spring is not changing at all. So if the block energy diminishes and the system energy, the entire system, does not, then what's happening to this energy here as the energy of the block slowly but surely diminishes? So that doesn't seem to make any sense. Um, we could say something similar about this third one, that the system energy seems to be diminishing, but the block energy never changes. And that could be true. I think just this by itself, the energy of the block could be constant if it was a vertical problem, and the energy of the block was both its potential and kinetic energy. So that could be true in that kind of system. But we've got a horizontal system where there's only kinetic energy and no potential energy. So somehow the energy of the block has to be diminishing over time. So that leaves us with just this last result here, which, let me slide this up. I guess my photograph didn't do it justice. I didn't capture the x-axis, but you know what that is. It's time. It's the energy of the block diminishing over time, and the energy of the block in the spring also diminishing over time. And not coincidentally, it starts off with something high, even though the energy of the block might be 0, the energy of the spring would be high, so their sum would be high, but as the inevitable effects of friction take over and make that smaller and smaller, you'll see that in the entire system of the block and the spring. So you don't see the oscillations because they're kind of complementary. As one peaks, the other one diminishes and so forth. But you do see the overall diminishment of the energy because of friction.